Welcome back to the Day 2 afternoon session of RAICT 2020. I'm profusely elated to take an opportunity to introduce Dr. Saurabh Shukla sir from Data Science Institute, National University of Ireland. So, have completed his PhD from University of Technology of Petronas, UTP, Malaysia, and Masters from Indian Institute of Information Technology, Allahabad. His research interests are Internet of Things, cloud computing, fog computing, blockchain, machine learning, communications network, algorithms, and artificial intelligence. So, has worked on fog computing project and have varied publications in journals of repute. Dr. Saurabh Shukla sir will enlighten us on data science, machine learning, Internet of Things, and cloud computing in today's session. Over to you, sir.
Thank you, Nasha ma'am, and it's a good opportunity to be a part of RAICT 20. And I'd like to thanks and to the Honorable Vice Chancellor of Integral University, to the Pro Vice Chancellor, and I want to thanks the Head of Department, Dr. Faisal, for inviting me for this special session for the benefit of the young researchers and other team members. I'd like to thanks the colleagues of Dr. Faisal and team for conducting this uh, fruitful session for all the researchers and the young aspirants to do research and have excel in the field of cloud computing, machine learning, because I think this session is basically related to machine learning and cloud computing. So without taking too much time, I'm going to share my screen for the today's session. Just give me a minute. So the today's session, which I'm going to speak, is related to health of Internet of Things and the role of healthcare Internet of Things in in minimizing an application of computing and its role in healthcare Internet of Things. So basically, nowadays, what we have seen that all the healthcare applications are going to be digitized. We have ECG monitors, we have pulse oximeters, we have blood sugar levels monitors. Even in the during the pandemic time, some of the people are using to check the oxygen level in their bodies. What will happen if I connect all these things with an internet, and through that internet, I can transfer the data or maybe the patient health data to a distant cloud server. So there is a possibility, and some of the hospitals they are doing in India itself also. But the problem is that the most of the data centers in India are mostly in the developed countries like Japan, Singapore, and some of the data centers in China, in Hong Kong also. And there is one center in Australia also, in which some of the healthcare provider services in India are connected to that. Now, the question comes, why we are talking about so much about healthcare IoT? If you can see, the current market scenario of healthcare IoT is around going to be $117 billion by 2020. That is this year itself. And around 30.7% of IoT devices found in healthcare and 69% are found in other sectors. It means out of 100%, 30%, more than 30% are IoT devices related to healthcare. So the zettabytes, the IoT is generating a very large amount of data, and it goes to be around 507.5 zettabytes of data by 2020. And the devices will be around 50 billion. So this is a challenge for the scientists and the researchers and the users maybe the doctors, patients, and the clients, how to monitor this data, how to analyze this data. Now, what is happening? When we talk about the quality of service requirement of e-healthcare services like robot surgery, and we want to measure the patient health data that is related to vital sign monitoring of ECG, then the maximum delay, the per packet delay, is for some real time monitoring is less than 300 milliseconds. Yes, it's less than 300 milliseconds. It means when the size of the data will increase, the latency or the delay, latency, it means the request and the response, the difference between request and response, it will increase. So that is a major challenge for the e-healthcare services right now we are facing, how to minimize the latency for real-time monitoring, for real-time robotic surgery, for real-time communication video-based, for e-healthcare purposes, communication audio-based, and there are quality of service requirement for every attributes. Now we have data rate and the maximum delay for audio, video, ECG. So depending on these requirements, the cloud data center is unable to fulfill because of few reasons. The problem is that this is the existing data transmission between healthcare IoT and cloud. This is the conventional data transmission. We have patients wearing wearable devices. They are connected to a local area network, and they transfer the data through different routers. Routers acts as the nodes connecting the cloud and the patients. When we want to transfer the data from India to, for example, a hospital in Lucknow, and that hospital is wants to transfer the data to some data center in Singapore, then there will be a multiple hop count. It means multiple hop count means if he wants to send the data from this patient to R1 router, it is the one hop count, R1 to R2 second hop count, R2 to, like this, there are many routers placed between Singapore and the Lucknow for the transmission. This will create a delay in the transmission of data. There will be a delay, that is the inherent processing delay inside the router itself. So the problem is that from local area network, we are going to wide area network. The benefits of having cloud data center is that they have a big data management, massive parallel processing, centralized cloud server. Although centralized cloud servers now facing issues due to single point of failure, and but now the drawbacks will be there will be high service latency. Service latency means when a client requests a service and then it gets the response a little late. There will be a network latency due to the last transmission of data, excessive workload for a particular cloud data center, multiple hop count, as you can see in the figure. So it will not be suitable for the real-time data transmission. There will be a round-trip time delay between the patient, that is who is wearing the wearable IP device, and the cloud data center for the request and response. So this is the conventional data transmission. So what we can do in this, we are not removing the role of cloud. Instead of that, we are supporting the cloud by introducing a middleware layer, which is called as fog layer. Although many publications have been done on this existing scenario, but there will be research is open for everyone. You can always add something and make it a little new in that. So this layer is added to give help to cloud data center and provide a single hop count communication to patients and doctors. So as you can see in the figure, a fog layer is placed between healthcare IoT and the cloud data center. So fog nodes, which is a part of the fog layer, will act at the local area network, that is at the edge of networks, and they can directly communicate with the healthcare IoT devices. So if you can see the figure, healthcare IoT is connected to the fog in a single hop count communication, whereas fog is also communicating with the patients or the users in a single hop count. These fog nodes are geographically distributed, and they are mainly for data analyzing, data pre-processing, filtering, and classification of data. That is, which data is a time-sensitive data and which data is non-time sensitive data. If the data is time-sensitive data, they are processed to be at the fog nodes. If it is non-time sensitive data, that is not sensitive data and not the non-real time data, it will transfer directly to the cloud. That is the historical data. So there are certain kind of algorithms which are working at the fog based on your choice or based on your implementation. You can uh, design an algorithm to classify the data in the fog node itself, and then you can assign certain roles to fog nodes, which we are going to see in other coming slides, that how they are transferring the data to the cloud and how they are assigning the role to the fog nodes and which simulator we are going to use. So this is a proposed uh, figure for the model that we have mentioned, that we are talking to solve the issue of latency between the healthcare IoT and the end user. So what is happening? I'm just going back to slide. What is happening? Rather than placing any server or a gateway to the Singapore, we are just placing the server or the gateway to the local hospital, to the nearby local hospital itself, so that they can communicate directly in a smaller hop count, and the data can easily transmit to the end users. So the problem is that with the cloud data center, as I've already mentioned, there's a large volume of data which is transmitted by healthcare IoT devices, a multiple hop count communication, and each router introduces a delay that is maybe a few milliseconds, and these few milliseconds can be a larger when we talk about a larger amount of data. That is, data can be in gigabytes. We have seen the zettabytes of data also. So with this increase of transmission of data, there will be chances of packet loss also, which increase to error. That if we want the data in 10 milliseconds and we are getting the data in 5 minutes, then there will be some tampering of data, or maybe some change in the values of some erroneous values of data. So that is the main issue with the cloud data center. So for the researchers, the question comes in the mind, because I hope many of you are working on this problem also, as I've gone through the pamphlet that some of you are presenting their paper related to fog computing and IoTs. So the question comes in the mind, how the fog computing can be able to control or regulate the data traffic rate, which creates the problem of network bottlenecks due to the increase in IoT devices, and how the algorithm, your design algorithm or your selected algorithm, will be able to know which task is to be handled by fog computing and which task they can transfer to cloud, because the algorithm should be intelligent itself to decide. It should be a decision maker, because fog node can be your laptop or your mobile device, and they have a limitation with the memory and the processing capacity. So you cannot process all the data in the fog node itself. You have to transfer some of the data to the cloud. So you should be aware which data is time sensitive data, so that you can process at the fog nodes, and which data is non-time sensitive data, or that is non-real time data, or we can historical data that we can transfer to the cloud data center. Next, how can we can meet the challenge to meet the requirement of quality of service for healthcare time sensitive applications, because healthcare needs the quality of service requirement, um, so that the requirements of users, patients, and doctors can be fulfilled. So these are the questions, and this is the proposed model. There are some of the existing techniques and technologies for comparison between the proposed model and the existing techniques. So we have in the past 2 years, many of the researchers have come with different ideas to solve the problem of latency and high and network delay. So there are some of the mentioned techniques. They have used some certain kind of machine learning techniques. They have used certain kind of offloading techniques. So even if you want to go through these techniques, you can also go through, so that you can have an idea what they are speaking about. Now, there is a kind of a three-tier architecture. It's a general basic architecture in which we have also introduced the model which I've shown in the previous slide. I'm trying to make it a more simpler one, that there is a one Fox layer in which there are fog gateways. A Fox server is divided again into multiple virtual machines. In these virtual machines, whatever the patient health data packets are sent by IoT devices, they are processed in these virtual machines, and they are going to decide based on the selected algorithm or the implemented algorithm that this is a time-sensitive data. So we are processing in this fog layer only, and that is a non real-time data. So that is transferred to the cloud data center. Now the user can access from the fog layer itself, and the user will access only the time-sensitive data, not the non-time sensitive data. So this is a system model in which basically a system model is going to more detail that the classification of data in this is done through fuzzy inference system, in which we have classified the data of low risk, normal, and high risk, and then we have allocation of these resources or the data packets to the virtual machines, and the selection of fog node. Because what will happen if you're transferring the data continuously, there will be a bottleneck. Many data packets are waiting for their turn to be processed. So we need to find which fog server is having a minimum computation latency. The role of computation latency is that the fog node itself is going to take minimum processing time to process the particular patient health data. So based on this model, the architecture, and the proposed model, we have implemented the algorithms, and the algorithms are further verified using analytical model also, because when you design an algorithm, you need to verify the algorithm mathematically also. To verify the algorithm mathematically, we have proposed analytical model also for minimizing the latency. But before to coming to that, because many of you, I came to some of the students when they have gone through my work, they have asking which kind of simulation tool we are going to use for this purpose, and which tools are available as a free of cost. So I have used iFoxSim, and it is easily free available, and you can easily also download and you can install on your system, and you can implement your algorithm in iFoxSim. It is basically part of a cloud sim. It works on Java, and designed by University of Melbourne, if I'm not wrong. And there are other tools also if you want to implement your algorithms in fog, like fog torch, fog torch 2, edge fog, and fog bus. So there are other similar tools for fog computing also, and depending upon your objective and needs, you can use them. I have used iFoxSim. So then there is a small comparison between the different users have used various kinds of tools and what are their roles. uh, you can also have you all of you can also go through all these the comparison between different modeling tools, and it is easily to use and easy to implement your algorithms, so you can get the result according to your design algorithm. So basically, I'm not going to much detail in my algorithm. I'm just going to give a brief what's the functioning of algorithm. So my algorithm is basically classifying the data, and after classifying the data, it is allocating the data packets to reinforcement learning and neural network, and selecting the patient health data. When selecting the patient health data, it allocates the data to that particular fog gateway, which is having the minimum computation latency. And from that fog, fog server, the user can access the data because that is the fog node which is having the minimum computation latency, and it contains the patient health data, which is a time sensitive data. So this is basically the functioning of algorithm. So I'm not going much details in this algorithm, because if you want to know about the detailed working of this algorithm, you can see my recent published paper on this, and how the simulator is working, and how the iFoxim is, because many of the students have questions that they are not able to use iFoxim properly. So you can have a detailed discussion on that iFoxim by going through my paper. So moving ahead with the analytical model, I'm not going much detail with this mathematical equation. I'm just going to the last slide. See what we have done. If you can see, there is reward is equal to 1 upon latency. When I have used reinforcement learning to solve Markov decision process, that is Q, so using Q learning. When we talk about reinforcement learning, we talk about the environment. The agent moves in the environment and takes an experience and performs an action. Based on its action, it gets the reward. So the concept behind the algorithm or the analytical model is that maximum the reward, minimum the latency. Because in our work, we want to minimize the latency. The minimum latency is our reward. So if we maximize the reward, naturally we are minimizing the latency. This is how the algorithm, this is how the analytical model is working. And at the last, we have proved that reward is inversely proportional to the latency. So we have maximum reward, it means we have minimum latency using in fog computing environment. So we have used data from UCI machine learning repository of ECG patient, and we have used iFoxim simulator in this, and we have used a fuzzy inference system. It's general systematic diagram how this fuzzy inference system is working. So we have inputs and we have the output, and then we have different range of the values. Next, we have further classified to minimize the number of variables. We have used principal component analysis of machine learning to minimize the number of variables. And after minimizing the variables, we have set up the GUI interface in iFoxim simulator, and we have different configurations of these simulations. We have master fog controller, we have fog devices, ECG IoT devices, cloud server. Data is transmitting from ECG to fog, fog to master fog controller, and then to cloud server. So this is a whole different configurations have different IoT devices. And with the increase in number of IoT devices, there is an increase in the latency also. So this we have shown through our simulation. And for to prove your simulation is correct, verify, you need to verify mathematically also by substitution and elimination method, and by using the qualitative techniques also, like standard deviation, mean, and regression analysis, t-testing. So if you are working on this direction, I just suggest you to work on the qualitative part of your research work also, and simultaneously work on the quantitative part of your work also. Quantitative part means you are working on the values which are getting displayed after implementing your algorithm in the simulation. And to verify that result, you do qualitative assessment. That is, you find the true positive, true negative values, and you find the standard deviation, t-testing, compare the results with other things. So this is the whole scenario. And then we have some results. These results are already mentioned. We have find the result for energy consumptions, execution time, and it is a quality of service comparison between fog and cloud using iFoxim simulator. And we have end-to-end latency, and then we have a benchmarking with the existing works. And this is the quantitative assessment of our work. And And this is how. Now, the question comes for other researchers who are working on this problem. What will be the future work for this? See, I'm talking about healthcare IoT data transmission in fog computing environment. But how secure the data is? There are many intruders. There are many IoT fog IoT devices connected in a heterogeneous manner. Someone is connected with ECG, some is connected with EEG, many heterogeneous devices. To tackle this problem, what will happen if the cloud data center becomes uh, becomes attacked by some intruder or hackers, or maybe the data sent by IoT is tempered, and maybe there is a single point failure of the data center? Then what will happen? So there may be in future, or maybe in the recent publications, I have seen that people now are using fog computing as a in a because it is a decentralized functioning fog computing with blockchain, because blockchain also work in a decentralized manner. So there will be a very good combination of fog computing with blockchain to provide reliability, security, and using different cryptographic operations for the secure data transmission for healthcare IoT and for healthcare IoT. Because what is happening, it is very difficult to identify the IoT devices, how authenticate the data generated from healthcare IoT devices, because then only the doctors and patients can rely on that data. So in the future, you can work on the integration of fog computing with the blockchain. And they have a major role in telesurgery, robot surgery, and telemedicine. So this is the thing from my side. And I just want to share one more thing. This is one of the paper that we have worked on this problem, that is analytical model to minimize the latency in healthcare and things in fog computing environment. So if you get time to look into this paper, you can get an idea and you can work in the future problem also. Thank you for my this presentation, and I think and I can pass the mic to Dr. Faisal. Or okay, thank you from my side. This is all from my side regarding the application of fog computing for healthcare Internet of Things. If anybody is interested to have any questions, he or she can ask.
Thank you, sir, for your valuable time and exemplary intellect. Thanks once again.
Thank you.
So, so this is the last live session of RAICT for today. We will be live again tomorrow for more sessions related to recent advancements in information and communication technology, followed by the valedictory session. The information regarding the tomorrow's schedule and session links are available on the website and have been communicated to you through emails and WhatsApp group. Have a great day. I thank you once again, Dr. Saurabh Shukla, sir, for giving your valuable time and your sharing your knowledge with us. And it will surely benefit our viewers and participants to understand things in a better way. Thank you, sir. We sign off.